Hello, this is Darren Pulsifer, Chief Solution Architect of Public Sector at Intel, and welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. On today's episode, we're going to talk about decreasing ingestion congestion using Intel Optane DC persistent memory. When I first found out about Intel's Optane persistent memory, it really got me excited about all the really cool things I can do with it as far as programming, and I really feel like it is going to change the way that we think about programming in the future. But one thing I didn't understand was all the versatility that it included, all the things I could do with it. And one of the things I tried to look at was how could I apply this new technology to existing problems that we have with some of our customers. And one of our customers was in the automotive industry, and they were having a hard time trying to figure out effectively getting information out of their cars and into their data center so that they could do machine learning or analytics on the data that they were collecting. And there's been lots of work done in this space, but it's primarily been research. It's been good for a small number of cars, maybe 10 or 100 cars. They were looking at 100 million cars. So how do I handle something that large? So if I look at their whole service stack and how everything was coming into the data center, it always pointed to this one thing, and that was data ingestion. How do I ingest that much data into my data center? And what can I do to figure out how to do this quickly? So I started thinking about, what can I do? What technologies can I use? And one of the things that we saw was that they wanted to use Kafka for their ingestion. And Kafka has been around for some time. It's used in the industry all over the place for basically a pub-sub-hub, a way of ingesting data in to a data center and placing the data in the most appropriate places that I can through something called topics. So as data comes in, I can assign it to a topic, which then could land in a stream with a whole data pipeline, or it could land in storage. It could do a lot of different things. But the key is that Kafka is this broker that can then handle several producers, put it on a message bus, and then different consumers can consume the data as it's coming in. And Kafka can scale really well. I can put several Kafka brokers to handle lots of data coming in to my data center or into my systems. So great flexibility, great tool to handle a lot of different producers, different consumers, and a lot of data. Now, Kafka was primarily developed for message sizes of about 1 to 10 kilobytes. That's not very big. And the kind of data we were getting out of cars was 240 kilobytes, approximately. Now, there's some tricks you can play. You can send a message that says that data has arrived, and then kind of like an envelope, data has arrived, and then point to where the data is and then move the data that way. Other tricks that we can play, but I wanted to bring the whole 240 kilobyte message into the Kafka bus so it could just move as I needed to. So I started looking at what other people were doing with Kafka to see if this would scale the way that I really wanted it to for my customer. So I looked at performance best practices that are out there. So some of the best practices that are out there are to manage your buffer size, so that I can handle multiple messages. And if my messages are all coming in about the same size, that works out well if they're exactly the same size, because then I can set my buffer size to always include whole messages instead of breaking them on half. So if I can increase my buffer size, I can move more data through. Also, batch size as well. I want to base it off of the message size for optimal performance. All these are like fine-tuned things that you can do with the type of data that you're bringing in. And then the other one that seems to be the most successful that people have is spreading the logs, which a Kafka log is really kind of a journaling log. It gives persistence to the data. So the data comes in and I put the data in different partitions or in different topics that end up in different logs. So this gives me a lot of flexibility. I can take a topic, break it into several partitions that I can span over multiple drives. So the key here that everyone talks about is how many drives am I spreading my Kafka logs over, and I want the fastest drives possible. So a great example, this example is a couple years old now, is what LinkedIn, they're published, so I don't know what their current numbers are, but their published numbers from a year or so ago was they can handle about 13 million messages a second, or 2.7 gigabytes per second. So for our customers, we kind of ran these numbers. With LinkedIn, they say they have about 1,100 Kafka brokers and more than 60 clusters. So it's a pretty big configuration. And if I look at what our customers were looking at, they had 100 million cars, 240 kilobytes per minute per car, which is only 1.6 million messages per second. So way under the 13 million, so that's not a problem. But it was 800 gigabytes per second that I need to ingest into the data center. So if I just took those raw numbers, compared it to LinkedIn's, which, is probably not optimized for 240K, I came up with 44,000 brokers. We're talking a lot of machines, right? So if I optimize it, I figured I could probably get it down to 4,400 brokers, which is still 240 clusters. That's a huge amount of machines. So we had to come up with another way to make things even faster, right? Now I could probably do even more optimization to get it down to maybe 400 or 500 brokers, but let's see if there's something else I could do. So I looked at our Optane persistent memory. Now, this is really cool memory. It fits in a DDR4 format, so it sits right on the DDR4 bus. It goes up, today, they can go up to 512 gigabyte modules. So in one 2-socket server, I can have 6 terabytes of memory. That's pretty cool. And it's persistent memory. So when I turn the machine off and turn it back on, it's still there. So I have the persistence that I need. There's a lot of really interesting things with this. It has hardware encryption built in, highly reliable, great technology, right? So I'm saying, okay, I got to figure out a way to leverage this new technology that is available to me to help solve this problem. So I first learned a lot about this Optane DC persistent memory. And I learned that there's 2 modes of operation. One is called app direct mode, and the other one is called memory mode. Now, memory mode is really simple. It basically, in memory mode, it uses the persistent memory as normal RAM, right? Because it's cheaper than normal DDR4, I can get more RAM into a system at a lower cost. And so I get some pretty good performance. It's not the same as DDR4, but it's pretty darn close. Close enough that in most applications, you're not going to see a difference. Now, in app direct mode, I looked at that, and in app direct mode, you can actually write from your program directly into persistent memory. So in most people, when they need something persistent, they write it out to a file system, right? So in this case, I don't have to, if I use app direct mode, I don't have to marshal and unmarshal my data structures and stream them. I can just push them into persistent memory, which is awesome, right? So there's also another thing I can do with app direct mode. I can actually mount it as a file system so that the OS sees it as a file system that I can write to. But it's not going over the I/O bus, it's on the memory bus, which is a whole lot faster than the I/O bus. So there's all the different things that I could do. So I thought, okay, let's take a look at this memory. What can I do with this memory? So I started looking in all the tools that are available. And there's 2 primary tools that are available using the Linux kernel, IndyCTL and IPMCTL. So IndyCTL is for creating namespaces for this new memory, this non-volatile memory that's out there. So it's a non-volatile memory device controller, right? And then there's IPM controller, which is Intel Persistent Memory Controller, which lets me manipulate and control this persistent memory. So I can set it up into different modes. I can set it up into memory mode or app direct mode, either way. So I had to learn a little bit about these tools and how they work. Let's take a look and see what I can do to make Kafka faster. So the first thing I thought, well, if I gave Kafka a lot more memory, it should run faster. My buffer sizes could be really large and I could really make this thing scream. And I said, it won't require any code changes at all to the Kafka configuration or just small Kafka configuration changes, right? And I can do that. So that's one option. The other option was, what if I changed Kafka? Instead of writing to a file system, what if I change Kafka to write to persistent memory instead? It'll be a whole lot faster. I just take the data and jam it into memory instead of take the data, marshal it a little bit, and then jam it out onto a hard drive. So I thought this would be it would be very fast and all that. And then the last thing I looked at was, why don't I create a persistent file system, right, using persistent memory and mount that and then put my Kafka logs on this new file system that's using my persistent memory. So I waded through all these. I looked at the Kafka code. I said, oh, I'm going to have to rewrite code in order to move it into production. It's going to go through approvals. And I thought, okay, that's longer term. We can look at it. The easiest one was the first one, larger memory. So that's the first thing I did was I ran all my tests with more memory and no change in performance. None whatsoever compared to running it with a smaller memory footprint and a larger one. No big change. And the reason why is eventually my buffers filled up and I had to write out to a drive. So eventually everything had to go to the Kafka logs, which obviously was my bottleneck. So I jumped down to number 3 and I said, okay, I'm gonna point the logs to this new ultra fast file system that I have. And the results were very fascinating. So that's what we're going to talk a little bit about, is what I saw and the results and how I did it. So one thing I did was I wanted to make sure I was testing the performance. My assumption was that the logs were the biggest bottleneck. And if I put it on an ultra-fast file system, I would get massive improvements. So I said, all right, what other things could get in the way of testing? So I knew network was going to be a factor. So I took network out of the equation by running my test on the same machine that my broker was on, right? And I only set up one broker. I didn't set up inter-broker communication because I just wanted to isolate what the impact of this drive would be on an individual broker. And then I only ran producers that were producing data in, and then I only ran consumers because I wanted to weigh the difference between the two. And then I ran a mixed so I could see what read and write would look like on this media. Okay? So I ran through all these tests. So my goal here was not to look at total production improvement, but an individual broker by itself and to see if this drive would really make a difference. So the first thing I did was I said, okay, I want some more memory. So I'm going to take half of my persistent memory and make it into app direct mode and turn it into a file system. And then the other half, I'm going to leave as memory. And we'll run this test and see how this works. So I use the commands ndctl and ipmctl, and I create namespaces, and I mount these file systems, and I go ahead and I run my tests. And I ran the tests over several different message sizes. And these message sizes, I was expecting certain optimization, primarily for 1K, because that's what it was primarily written for. And I saw some interesting things on the number of producers that I had. I got better and better performance to around 10 producers, and then I started saturating the bus, right? I started seeing that I was saturating, but I was getting some really, really good numbers out of here. And I said, okay, very cool. All the numbers are looking very consistent up to 10. Past 10 producers, I started getting some wonkiness, some variability. So that tells me I was caching things. And so, but I was getting some pretty good numbers that I could now compare to running what I ran before on just a SATA drive for my Kafka logs. And then I also tried our Optane NVMe drives for our Kafka logs. So let's take a look at what those, differences are. So for 240 kilobyte, I took a normal SATA drive, and you can see right here, this normal SATA drive, pretty flat. I got some improvement, and then it decreased as the number of producers came up. When I use our Optane NVMe drive, I also got a nice peak, almost twice as fast as a SATA drive, which is what I would expect. It's an NVMe bus instead of a SATA bus. And then when I do the PMIM, look at that. A PMIM is almost 5 times faster than a SATA drive, and almost, 2.5 times faster than the Optane NVMe drive. And that's because of the bus. I'm using a memory bus instead of the I/O bus, the SATA bus or the NVMe bus. So big differences. The media could handle it fine, but the bus was my limitator. Okay, so I would quickly, this was running so much faster than what we were used to. I was quickly filling up this temporary drive, which was only 750 gigabytes. So I filled it up pretty quick, and I decided I need to run this a little bit longer. So I went back and I reconfigured my machine to do 100% app direct mode, so that I could now take the whole 1.5 terabytes. So I could run the test longer to see if there was any time when things dipped down and I was losing performance. So I reconfigured it, and I ran the same tests. And I got this really weird result. All of a sudden, I could add more producers. And my throughput almost went up another 2 or 3 times. When you look at those numbers, it's almost 3 more times. So now I'm sitting at between 12 and 15 times faster than a SATA drive at 25, 30 producers at 240 kilobyte message size. And this is incredible, right? Remember my problem at the beginning? All of my customers had so many brokers that they needed, which was, rows and rows of machines. Now I can put 15 times more than a SATA drive. I can decrease even more. It was incredible. In fact, I ran the test several times because I didn't believe the results that I was getting. And then I actually called one of our architects that designed this technology. And what I found out was, why did things run so much faster? Well, one of the reasons they ran so much faster is because before I was using part of my persistent memory as memory, and the other part is direct access as a file system. So anytime that I wrote, it would write into the persistent memory, into the DDR4 cache, back out, and then back over around. So, which is about 2 or 3 hops for the same data to go through. And in this way, I went directly into app direct mode, and that's where we saw the increase. Less contention on the memory bus, and my throughput went up dramatically. Okay, so the end result here was we were able to use Kafka with DC persistent memory as an ultra-fast file system to get major improvements in our throughput on both the producers and the consumers. Not a problem either way. I got similar results on producers and consumers. And then probably one of the biggest ones was the mixed mode. And most of you guys that are used to like SATA drives, especially SSDs, you know that writes are much slower than reads. Now, one really cool thing about Optane is its read-write parity as far as speed goes. So we did not see a major decrease. We saw what we would consider a normal decrease in performance when I'm running both at the same time. I wasn't getting, that total throughput on all producers or total throughput on all consumers, but I saw about a 10% degradation in total speed by running everything at the same time. I had 40 producers and 150 consumers, and I got really great speeds out of this. Thanks for listening to Embracing Digital Transformation today. If you liked our episode, go ahead and give us 5 stars on your favorite podcast or video streaming site. You can also find out more on embracingdigital.com. Until next time, keep moving forward and embrace the digital revolution.